Ever had that moment like you're racing against the clock, boarding pass, got to print it, 5 minutes to spare? The printer's like, nope.
Oh, yeah. The dreaded blinking light of doom.
Exactly. Today, we're diving into the stuff that makes our tech tick, but that we rarely think about.
Right, like the behind-the-scenes magic.
It's all about device drivers. We're using this operating system's textbook to, break down how these little bits of software actually make our digital lives, well, work.
It's funny you should mention that language barrier analogy because that's actually at the heart of why we even need device drivers. So your computer's operating system, it's got its own way of sending commands to the hardware, right?
Makes sense.
But here's the thing. Every single device, whether it's your mouse or your graphics card, they might have their own quirky way of understanding those commands.
So it's like needing a translator just to get the keyboard to talk to the monitor.
Kind of. And that's where our little friends, the device drivers, come in. They're like the interpreters of the tech world, making sure everyone is speaking the same language.
Okay, so how do they actually do that? Like, is it a direct translation or is there more to it?
Well, some are pretty straightforward, like taking the signal from your mouse and telling the operating system, hey, move the cursor over here. But others, like the ones dealing with your graphics card, they actually have to do a lot of interpretation and processing. It's less about word-for-word translation and more like conveying meaning.
So it's getting pretty nuanced. The textbook uses the phrase uniform access to various devices. And I'm realizing it's not just about making things universally compatible, it's about managing all those different ways devices communicate.
Exactly, and that's where things like communication protocols come in. Think of them like established languages that devices use to talk to each other.
Okay, that makes sense.
The textbook mentions USB and Bluetooth. Good examples of standardization, right? Makes everything work smoothly, ideally. And this is where it gets interesting. This whole drive for standardization is always butting heads with new tech development.
Oh, right, because the second we have a standard, someone's got to invent something even cooler that pushes the boundaries.
Yeah.
So, like, how do device driver developers keep up?
It's a tightrope walk, really. They've got to make drivers that work with older devices, but also be flexible enough for the new stuff. That's where APIs come in those application programming interfaces. They're like standardized instruction manuals that help developers write drivers for different types of hardware.
Ah, so a common language for the developers themselves. Makes sense. But what about when a device doesn't have a generic driver? Does that ever happen?
It does, and that's when you need those manufacturer-specific drivers. Sometimes companies make their own to squeeze out the best performance or add unique features. The downside: compatibility issues. Ever upgraded your operating system only to find you need a specific driver?
Oh, totally. Many times. So for our listeners who might not be, coding wizards, why should they care about device drivers?
Even a little knowledge goes a long way. It helps you troubleshoot problems, make better decisions when buying new gadgets. Plus, you start to appreciate the sheer complexity behind making this technology feel seamless.
It's like knowing a bit about how your car works. Even if you're not a mechanic, it helps when something goes wrong.
100%. So, here's something to ponder. Gadgets are getting smaller, more interconnected by the day. What does that mean for device drivers in the future?
Good question. More specialized. Or maybe a totally new approach to how hardware and software talk to each other.
Right, it's something to think about.
So next time your printer throws a fit, at least you'll have a little more insight into the hidden world of drivers working hard to, hopefully make things run smoothly.
Hopefully.
Thanks for listening, everyone. Ever hit a key on your keyboard and wonder, how does that letter actually get on the screen? Or how about when you're streaming a movie? How does it even work? Where does that data go? Well, get ready to dive deep, because today we're all about I/O hardware.
It's really the hidden language of computers, how they talk to the outside world and how we talk to them.
And believe me, it's a lot cooler than it sounds. We're going to untangle ports, buses, controllers. It's a whole symphony going on behind the scenes of your device.
And that symphony, it determines how fast your games run, even like the speed of scientific discoveries. It all boils down to how well data can move in and out of your computer, input, output.
So efficient I/O, kind of a big deal then.
Absolutely. Imagine your computer's like a busy city, right? Data needs to get around quickly, just like people going to work or getting deliveries. That's where I/O comes in. It's the transportation network.
Okay, I like this city analogy.
Yeah.
So what are the streets and highways of this digital world?
Ports, buses, and controllers. And actually, the source material breaks this down really well. It calls ports the bus stops, which I think is a great way to visualize it, like physically where things plug in, your USB, HDMI, even that old parallel port. Remember those?
Oh yeah, the parallel port, the dinosaur of connections. But hey, it worked.
It did. And just like in a city, different ports handle different traffic. Our source talks about PCIe, that's Peripheral Component Interconnect Express. Think of that as the express lane for data. That's how your graphics card connects. Those super fast transfers, especially with those 8-lane ones, those are really powerful.
That's why when you're getting a new graphics card, a good PCIe slot is key for those amazing visuals.
Exactly. And then there's your expansion bus. That's more like your local routes. Handles the slower devices, not as glamorous, but essential. Keyboard, mouse, that sort of thing.
Okay, so we've got express lanes, local routes. What else is in this city? The source material mentions something called SCSI. Honestly, it sounds like something out of Star Wars.
It does have a ring to it, doesn't it? It stands for Small Computer System Interface. And it's not as well known as, say, USB, but it's a real workhorse in data centers and high-performance computing.
So when we're talking about like streaming services handling millions of viewers or huge databases, that's where SCSI comes in.
Exactly. It's known for speed and handling tons of data really reliably, especially for storage area networks, which are common in those big data centers.
Interesting. So we've got data zooming around on these highways, but how are the devices actually using it once it gets there? They don't have their own little hard drives, do they?
You're right. They don't have separate memory banks or anything, and that brings us to a really cool aspect. Memory mapped I/O. Get ready for that aha moment.
Hit me with it. I'm ready to be amazed.
They're basically borrowing memory from the computer. Like, think of it as checking into a hotel, right? You get to use the room, but you don't own the whole building.
Okay, renting some memory real estate. I like it. But how does that actually work, the technical side?
So that's where memory mapped I/O comes in. Our source talks about it as mapping a device's control registers into the computer's address space.
Control registers. That sounds kind of complicated.
It's like this. Imagine each device has its own mailbox, right? Or a little register. And that lives within the computer's memory. There's one for status updates, one for data coming in, one for data going out, and one for control signals. It's how the CPU and the device can talk to each other by leaving messages.
So a super fast inter-office memo system for data. Okay, I think I'm getting it. But that makes me wonder, with all these devices sending messages, asking for stuff, how does the CPU, the big boss, keep up with it all? Seems like it'd be overwhelming.
It's true. Managing those requests, that's a huge part of I/O. And that leads us to the world of polling and interrupts.
Okay, now those sound interesting. Tell me more.
Imagine you're in a busy restaurant kitchen, right? The chef, that's our CPU. Now imagine if they had to constantly check with every single waiter if their tables were ready to order. That's polling. Not very efficient, wastes a lot of time checking on devices that aren't ready.
So like constantly hitting refresh on your email, hoping for a new message. No wonder it slows things down.
Exactly. But now imagine this. Instead of checking all the time, each waiter has a little bell they ring when they need something from the chef. That's an interrupt.
Ah, much better. The chef can focus until there's an actual order. So an interrupt is like the device sending up a flare. Hey, I need something over here.
You got it. And get this, our source says modern computers, they handle hundreds, even thousands of these interrupts every second. Constant stream of requests. But there's a system, thankfully.
Otherwise, total chaos, right? So how does a CPU know which interrupt to deal with first? They can't all be equally urgent.
You're right, and this is where it gets clever. There's something called an interrupt handler, which is basically a chunk of code that tells the CPU what to do for each specific interrupt. It's like a pre-programmed response to each bell ringing.
So like bell A means the oven's ready, bell B, we need more flour, that kind of thing.
Exactly. And all these handlers are organized in a table. It's called an interrupt vector. CPU can access it instantly. Super efficient for prioritizing.
Amazing how much is going on, just so we can look at cat memes without a problem.
Yeah.
But speaking of a lot going on, what about when you're transferring huge files, like downloading a whole game? Surely the CPU can't be dealing with every tiny bit of data then.
Definitely not. That'd bring everything to a halt. And that's where direct memory access comes in. DMA.
DMA. Sounds important.
Think of it like this. You're moving a ton of stuff. You wouldn't want to carry every single box yourself, right? You'd hire movers. DMA is like that. Instead of the CPU handling each piece of data, it hands it off to the DMA controller.
So the CPU is the foreman, telling the DMA crew where to pick up and drop off the data.
Perfect analogy. Our source talks about DMA command blocks. Those are like the moving instructions. The CPU says, hey, take this chunk of data from here to there, and then the DMA controller handles it. Frees up the CPU to do other things.
That is seriously smart. But if the CPU isn't managing the transfer, how does it even know when it's done? Is it checking in constantly with the DMA controller?
That's where it gets even cooler. Remember, interrupts. The DMA controller can actually interrupt the CPU when the transfer is finished. It's like the mover sending a text saying, all done.
That is brilliant. Like a self-managing data transfer system. No wonder our computers can do so much at once. This is blowing my mind, honestly. Data on buses, devices, renting memory, interrupt handlers. It's like this whole choreographed dance happening every second inside our machines. But something tells me there's more to the story.
Oh, absolutely. We're just scratching the surface here. We haven't even gotten to the software side, how the operating system manages all this hardware and keeps everything running smoothly.
Let's save that juicy bit for the grand finale. Back in a moment, folks, to meet the conductor of this data symphony.
And we are back. So we've explored these hardware highways, right? We met the DMA movers, even got a taste of the interrupt drama. But who's actually calling the shots in this whole data symphony?
That would be the unsung hero, really. The operating system, the OS, the software that makes sure all this hardware plays nice together.
So it's like you could have the most amazing kitchen, right? Top of the line, everything. But without a chef, it's just a bunch of fancy appliances. Exactly. The OS, it's the head chef. Coordinating everything, managing resources, making sure your applications, those are like the diners. They get the data they ordered fast and efficiently.
Okay, I can see that. But how does it actually DO all that? We were talking about DMA taking the load off the CPU for big transfers. Where does the OS even fit in there?
Remember those command blocks we talked about? The instructions for the DMA controller? Well, the OS is the one writing those, handing them off.
So the OS is putting in the order with the moving crew.
Yep. It's all about delegation. Think about it. Every time you save a file, open a program, even move your mouse, the OS is working. Managing those interrupts, allocating memory, making sure data fits between the hardware and what you're trying to do.
It's kind of wild when you realize how much is happening just so we can click a button and it works. But then that makes me wonder, if the OS is handling all these requests, how does it decide what to deal with first? Does it ever get overloaded?
Great question. And it goes back to those interrupt handlers. The OS sets those up, manages them, makes sure the most important stuff goes first, like a triage system in a hospital, you know?
So it's like this nonstop game of digital Tetris, fitting in interrupts, data transfers, everything all at once.
Pretty much. It's really amazing what software engineers have done, honestly. Our computers handle so much complexity and so fast, it's incredible.
I'm starting to think my computer deserves a raise after all that. But seriously, this deep dive, it's been eye-opening. I had no idea how much was going on under the hood.
It's a hidden world, but a fascinating one once you start to peek behind the curtain.
Well, and it's always changing. New tech, new approaches. We'll have to do another deep dive soon to keep up.
Always more to explore.
But for now, listeners, next time you see that spinning wheel of doom or your computer's acting up, take a second to think about all that intricate stuff we talked about.
Might give you a new appreciation for what's really going on.
Until next time, happy computing, everyone. All right, so have you ever tried to print something super important, and your printer just decides, nope, I'm going to print blank pages now. That's what I want to do. Or even better, it just spits out what looks like hieroglyphics instead of, your document.
Happens all the time.
Yeah, we've all been there. It's like, what is even happening behind the scenes with our tech?
Right.
And that's exactly what we're diving into today. We got some excerpts from an operating systems textbook, the real nitty-gritty stuff, and we're going deep, deep into the world of input-output and, get this, device drivers.
Yeah.
But don't worry, we're going to keep it fun, I promise.
I mean, it's funny how often we use all this tech, but we don't even think about how our computer actually talks to it, right?
Right.
Printers, cameras, keyboards, those VR headsets everyone's suddenly so into.
Yeah.
It's like they all speak their own language.
It's like magic. But our source material actually uses a really cool analogy for this. Imagine plugging in a lamp, a blender, your phone charger, all into the same outlet.
Oh, chaos.
Total chaos.
Yeah.
And that's kind of what our computers are dealing with every single day.
That's the challenge. Yeah. How does everything just work?
Well, the operating system, that's the key. It's like this universal adapter. It takes all those different devices with their different ways of communicating, make sure they can all plug in and work without turning your computer into a brick. Okay, that makes a lot more sense. But let's break it down a little bit more. How different are these devices? Our source material has this table, figure 12.4.2, and it lists out all these device characteristics. It's actually kind of mind-blowing how much variation there is. Like, you've got some devices that send data just 1 byte at a time, like your keyboard, and then others that are handling these huge chunks, like hard drives.
Yeah.
It's like, I don't know, reading one word versus reading a whole chapter of a book at once.
Yeah. And even the way they access that data is different. You've got sequential access. Think of like listening to an old cassette tape. Gotta go in order.
Oh, yeah.
But then you've got random access. That's like a DVD. Jump to whatever scene you want.
That's a great analogy. And don't even get me started on the speed differences. We're talking everything from like those old dial-up modems, took an eternity to connect.
Oh, I remember those days.
To these blazing fast SSDs that can transfer like a whole movie in seconds. How does the operating system keep up with all of that?
That's where the beauty of abstraction comes in.
Abstraction.
Yeah. So if you look at figure 12.4.1, it shows how the operating system is set up in these like layers of software, and each layer hides the really complicated details from the layer above it.
So instead of my computer needing to understand every single detail of every single device, it's got this simplified, standardized way of talking to them.
Exactly. It's like having a universal translator so you can speak any language in the world.
Okay, so who or what is the universal translator in my computer?
That, my friend, is the device driver.
Device drivers. Those are the things we only really think about when something goes wrong, like, oh, my driver's busted.
Right. But they're quietly working their magic all the time.
They're like the interpreters, constantly translating between what our computer speaks and what our printers, mice, webcams, you name it, what they speak.
Without them, our tech lives would be constant frustration. They are the unsung heroes making sure everything plays nicely together.
So device drivers, they're like the interpreters, making sure our tech doesn't descend into total anarchy. But here's where it gets really interesting. Our source talks about these things called escape hatches, and they sound kind of...
Well, a little bit risky.
Yeah. Like a backdoor into the operating system.
Right.
Basically, ways for developers to add new features or support for the latest, greatest gadgets.
Yeah.
Without having to rewrite the whole operating system.
Yeah, it's essential, though, if you think about it. That's how we get all the cool new tech. It's like, imagine you have a really well-established routine, but you want to add something new, something unexpected, so you slip in this little secret handshake, right?
I like that. Okay, so it's like sneaking in new functionality through the back door.
Kind of. And the routine stays the same, but that handshake, that's what changes the game. And a perfect example of that is this thing called the ioctl function. It's a little technical, but basically it lets a program and a device driver talk directly, exchange like special instructions or data.
So the secret handshake has its own secret language.
Exactly. And the cool thing is, this lets developers make custom commands for their devices. So stuff that no one even thought of when the operating system was first created, now it's possible.
That's how we're able to use all those new VR headsets, all those crazy gadgets that just seem to appear out of nowhere, right?
Exactly. It's all thanks to those clever escape hatches and the developers who know how to use them.
It's brilliant. But I gotta say, I also see how it could be a bit of a security risk. If there's a backdoor into the system, couldn't someone, with less than notable intentions use that?
Oh, absolutely. Security is a huge concern. It's a real balancing act, innovating while keeping things safe. But that's probably a whole other deep dive.
Okay, fair enough. Let's get back to those different types of devices. Our source keeps mentioning block devices and character devices, and I'll be honest, they always sound a bit like something out of a science fiction movie.
Yeah, I get that. Not the most intuitive terms, but they're actually pretty straightforward once you get the hang of it. Think of it like this. Imagine a really fancy multi-course meal.
Okay, I'm listening.
That's your block device. Appetizer, main course, dessert, all in a specific order, just like how a hard drive reads and writes data in blocks.
Okay, so what's a character device then? Is it like the opposite?
In a way, think about those conveyor belt sushi restaurants. Each plate comes down the line one by one. You just grab what you want when you want.
Yeah.
Like, that's your character device. Data flowing one character at a time, just like from your keyboard or your mouse.
Uh-huh. I'm starting to see it. So it's all about how the data is delivered, like a structured meal versus, I don't know, an all-you-can-eat buffet.
You got it. Now you're ready for another tech trick that sounds way more complicated than it actually is.
Hit me. I'm feeling like an operating system expert over here.
All right, let's talk memory-mapped files.
Sounds intense.
Right, like something straight out of the Matrix. But it's actually pretty clever. Imagine you've got this massive blueprint spread out, but you only need to work on a tiny little section. Now, instead of running back and forth every time to check the original, what do? You make a copy.
Makes sense.
Exactly. That's basically what memory mapping does. It takes the data you need, makes a temporary copy in your computer's RAM, which is super fast, so it doesn't have to keep going back to the hard drive, which is much slower.
So it's all about efficiency.
Exactly. Like creating shortcuts in the real world to save time. In the computer world, that translates to faster processing, smoother user experience.
It's amazing how much thought goes into stuff we take for granted every single day.
Right. And speaking of clever ways to deal with data, even networks have their own special way of communicating. Did you know that?
Oh, right. Our source mentions something about sockets. Are we talking about the same kind you plug your lamp into?
Not quite. For computer networks, think of a socket more like a virtual phone line between two computers.
Okay. Yeah.
That's how they exchange all those little packets of data, all those ones and zeros that make up, well, everything we do online.
So instead of electrical signals through wires, it's data packets zipping through the internet.
Exactly, like sending digital letters back and forth. And those sockets, they're the mailboxes, making sure everything gets to the right place.
Okay, I think I'm starting to see the bigger picture here. But there's one more piece of the puzzle I'm curious about. Clocks and timers. Like, I get that computers need to keep track of time, but how does that tie into all this I/O stuff we've been talking about?
It's a great question. And it might seem less obvious at first, but clocks and timers, they're involved in all sorts of I/O operations.
Really?
Yeah, they're like the conductor of an orchestra making sure everything's in sync.
Give me an example.
Well, think about setting an alarm on your computer. Seems simple, right?
Right.
But that alarm going off at the right time, that relies on the operating system's clock and timer system working perfectly behind the scenes.
So it's not just about keeping track of what time it is. It's about making sure things happen in the right order at the right time.
Exactly. And it goes even deeper. Think about something like online gaming.
Oh, yeah.
Even the tiniest delay, a little bit of lag, can be the difference between victory and defeat. Or streaming a movie, the audio and video have to be synced perfectly, or it's just, ugh.
The worst.
Clocks and timers are working behind the scenes to keep those data streams flowing smoothly.
I never thought about it like that. They really are the unsung heroes of the digital world, making sure everything runs on schedule.
And the more we depend on real-time data, all these interconnected devices, the more critical those precise timing mechanisms become. But let's not get ahead of ourselves. Still much more to uncover in this deep dive.
You know what really gets to me? When my text slows to a crawl, you know?
Oh, the lag.
The lag, it's like the digital version of being stuck in line forever, just staring at the screen like, hello, anyone home?
I know, it's brutal. And often those frustrating lag moments all come down to how the operating system is handling, like all those requests, all those different devices and programs, all wanting its attention at the same time. Our source material actually goes into two main ways it deals with this. Blocking and non-blocking I/O.
Okay, I am all ears. Tell me more.
Okay, so imagine you're at the post office, right?
Okay.
You need to send a package. With blocking I/O, it's like you are stuck in line until that postal worker is done with the person in front of you, no matter how long it takes. You can't do anything else.
Oh, that sounds awful.
It's the worst. And that's kind of like what's happening in your computer sometimes. Everything else has to wait.
So that's why it feels like it's frozen. It's waiting for some invisible task to finish.
Exactly. Now imagine if the post office was way more efficient, right? You drop off your package and then boom, you're free to do other stuff while you wait. That is non-blocking I/O. The system can keep working on other things while it waits for those slower operations to finish up.
So it's like multitasking for computers. That's got to be why some apps feel so much faster, so much smoother.
Exactly. Developers, they really have to think about this stuff when they're designing software. It can make or break the user experience. You don't want your app feeling like that slow post office line, right?
Absolutely not. It's all about making things, just work.
Right.
And speaking of which, our source mentioned something called, get this, vectored I/O. Is that another one of those make it work better things?
You bet. Okay, so imagine you're a chef, right? You need to gather all your ingredients. Instead of going back and forth to the fridge a million times, getting one thing at a time, what if you just loaded everything onto a tray and brought it all over at once?
Way more efficient.
Exactly. That's vectored I/O. The operating system can move multiple chunks of data in one go, less overhead, speeds up the whole process.
So it's like streamlining data, like optimizing your cooking workflow.
You got it.
Yeah.
And it's those kind of innovations that make the difference between a computer that feels, ugh, and one that's just like whoosh.
I'm honestly amazed by all the complexity happening behind the scenes of the tech we use every single day. It's like this whole hidden world.
It really is, and it just keeps evolving.
Makes you wonder, what's next for all this stuff? For I/O and device drivers. I mean, are we even going to need them in the future? Everything's moving to the cloud. Connections are becoming more standardized.
It's a good question. I think a lot depends on how fast those transitions happen and how creative developers get with all this new tech. It's an exciting time.
It really is. Well, unfortunately, that's about all the time we have for today's deep dive into, well, the fascinating world of device drivers. Hopefully next time you have a tech headache, you'll have a little more understanding, a little less arc.
And maybe even some appreciation.
Exactly. It's amazing how a little knowledge can turn frustration into fascination. So until next time, keep exploring, keep asking those questions, and never stop being curious about the amazing world of tech all around us.
Ever walked past a restaurant kitchen and just kind of stopped to watch? It's mesmerizing, right? All that hustle and bustle, but it works somehow. They're getting orders out, and I'm here for it. That's kind of what I think about with the I/O system on a computer, you know?
It's the hidden world that makes everything run.
Exactly. And this deep dive, we're going all in on the kernel I/O. We've got some seriously detailed excerpts here, pulling from chapter 12.5 of this. That's a whole technical document on operating systems. Really gets into the nitty-gritty.
The kernel I/O subsystem, yeah. Most users, they don't even realize it's there, but it's essential. Like the unsung hero of your digital experience, right?
100%. It's the maestro making sure your applications and hardware aren't just playing random notes, but actually making beautiful music together. But look, our source material, it goes deep. We're talking like PhD level stuff at times.
Yeah, it can get pretty dense.
So what we're going to do is pull out the good stuff, the stuff that matters, whether you're a coding whiz or just curious about what makes your computer tick.
And there are some really clever tricks this system uses to keep things humming along. Like, did you know it actually prioritizes tasks?
Oh, you mean like I/O scheduling? Yeah, the source material really dug into that.
It's all about efficiency. Think of it this way. Imagine a waiter weaving through a packed restaurant, right? If they're zigzagging all over the place for every order, it's chaos.
Total inefficiency.
But a good waiter, they're optimizing their route, delivering orders in a way that minimizes wasted steps, right?
So the OS is like the head waiter for your data.
Sort of, yeah. It decides what gets handled first, how to group similar requests.
Yeah.
It's all about minimizing something called disk thrashing.
Disk throws.
So with older hard drives, the ones with spinning platters, the order of requests actually makes a huge difference. It's about how much that little arm has to move to read the data.
So if the requests are all over the place, it's like
A cat chasing a laser pointer? Exactly. Frantically searching all over those platters slows everything down. But efficient scheduling. The arm moves smoothly, gets the data in a much more organized way.
Okay, so that's why my computer sometimes lags. Even when I'm not doing anything too crazy. Could be bad I/O scheduling.
Could be, yeah. Especially if you've got a lot of programs running,
Oh,
all needing disk access at once. And this isn't just hard drives, by the way. I/O scheduling, it's for everything. Your SSD, your network card, even your USB ports. It's all about keeping those data highways clear.
that's wild. Okay, so we've got scheduling down. What about buffering? That one always kind of trips me up.
All right, so let's stick with our restaurant analogy, right? You're the chef, orders are piling up faster than you can cook. What do you need?
A bigger kitchen.
Well, that wouldn't hurt. But what you really need is a good system, like a holding area where orders can wait their turn.
Okay, so like a staging area.
Exactly. And that's essentially what buffering is, a temporary storage space where data hangs out until it's ready to be processed.
Okay, so is it about speed then?
It's part of it, but it's more about managing the flow, making sure everything's running smoothly. Take streaming a video, for example. The data is coming in from the internet, which can be a little, shall we say, unreliable.
Oh, tell me about it.
But the reason you can still watch that video without it looking like a slideshow, buffering. Your computer's downloading chunks ahead of time, storing them in a buffer, so even if your internet hiccups for a second.
I don't notice a thing.
Exactly.
That's incredible. I had no idea that's how that worked. So buffering is like the smooth jazz of the data world. Just keeps things nice and mellow, even when things get a little hectic behind the scenes. Okay, buffering smooth jazz. Kind of like that analogy. But now I'm curious about caching. How's that different? It seems like they're both about, holding on to information for later.
Yeah, they're related. But caching, that's more like having a VIP line for your data. Remember our restaurant?
Of course.
Let's say you've got that one dish you order every single time. Instead of making it fresh every time, what's the chef going to do?
Keep a few ready to go.
Exactly. Save time, keeps the customer happy, and that's caching in a nutshell. Your computer stores frequently access data, things like files from applications you use all the time, in a special spot. Really fast storage called RAM.
So next time I open that app.
Boom, instant load. Or close to it, anyway.
Okay, so caching is about speed, and buffering is more about maintaining that smooth, consistent flow. Did I get that right?
Nailed it. They work together, though, really make your computing experience what it is. Speaking of working together, our source material also dives into another key aspect of the I/O subsystem, coordination.
Okay, so it's not just about how fast it can move data, but also how well it keeps everything organized.
You got it. Let's go back to the restaurant one last time. Imagine, even with the best chef, the fastest waiters, what happens if there's no coordination?
Complete chaos. Orders get mixed up, food gets cold.
Disaster. And that's where something called spooling comes in. Remember seeing that in the source material?
Vaguely. Didn't quite click for me at the time.
Right, so spooling is a perfect example of the I/O subsystem playing traffic cop.
Yeah.
Say you need to print something huge, like a gigantic menu for our restaurant, but at the same time, someone else is trying to print a quick email.
Without spooling, it'd be a mess.
Total mess. Spooling creates a queue, a buffer, actually, on your hard drive for those print jobs.
Ah, so everything comes out in order.
Exactly. No more jumbled pages, no more printing on the wrong paper, that little printer queue icon that pops up.
That's spooling doing its thing.
Yep. Simple concept, but crucial for making sure shared resources don't descend into chaos. Shows you the I/O subsystem, it's involved in way more than just moving bits around.
Speaking of things not always going smoothly, what about errors? The source material, it actually had some pretty fascinating stuff about how the I/O subsystem handles those.
Right, because even in the best restaurant, sometimes things go wrong. Orders get missed, a dish gets dropped, maybe the power flickers.
Oh yeah, you gotta be ready for anything.
And that's what the I/O subsystem does with digital errors. Dropped internet connection, a corrupted file, even just a temporary hardware glitch.
It's like the I/O subsystem is on damage control.
Always. You might retry operations, reroute data, even isolate a faulty component, to prevent things from getting worse.
So like when my hard drive does that little thinking pause sometimes.
Could be the I/O subsystem hard at work back there, trying to fix a problem you didn't even know you had.
Wow. I had no idea. But here's a thought. If the I/O subsystem is so busy fixing stuff, why doesn't it too? Tell us more about what's going on.
Interesting, right? The source material actually touched on that. It's like it cleans up the mess, but doesn't want to bother you with the detail.
Less panic that way, I suppose.
They gave this example of SCSI devices, which are pretty common for hard drives. Apparently, those things can give super detailed error reports, like down to the specific component that's acting up.
But most operating systems, they keep it hush-hush.
Pretty much.
So it's like, they know we can't handle the truth. Just give us the simplified version.
Something like that.
Right.
Although, it does make you wonder, how much information is too much information, I mean, do you really want a pop-up message every time a single sector on your hard drive has a little hiccup?
Probably not. I can barely keep up with the notifications I already get.
Exactly. Too much detail, it just becomes noise. But too little, and we're left in the dark. It's a balancing act for sure, something operating system designers are always grappling with.
It's like, I appreciate a good waiter who can explain the specials, but I don't need a lecture on the history of every ingredient.
Right. Sometimes you just want to enjoy the meal. Speaking of things we don't always think about, our source material also went into the I/O subsystem's role in security and power management, which, at first glance, don't seem that related to, input and output.
Yeah, I was wondering about that too.
They're more connected than you might think. Okay, so security. Think of it this way. In our trusty restaurant analogy, security is like having a good bouncer at the door. You don't want just anyone wandering into the kitchen, right?
Headed straight for the walk-in.
It's exactly chaos. So the I/O subsystem, it's like that bouncer for your computer. Make sure applications have to go through the proper channels. They can't just access whatever data or hardware they want.
Okay, so how does it actually do that? Like, what's stopping a rogue program from just going around the system?
Well, the source mentions something called privileged instructions. These are like special commands, and only the operating system is allowed to use them. It's like the master key to your computer's hardware.
So any program that wants to access something sensitive, it has to go through the OS first.
Exactly. No more sneaking in the back door. Which, speaking of sneaking, Let's talk about power management,
Mm.
because the I/O subsystem plays a big role in that too.
Hmm.
And I'm guessing you care about battery life, right?
Oh, absolutely. Especially on this thing gestures vaguely at recording setup.
So, back to the restaurant one last time, I promise. Imagine it's that lull between lunch and dinner. Does the kitchen staff really need every single oven and burner going full blast?
Huge waste of energy.
Right. And that's what the I/O subsystem does for your computer. It can tell certain components to power down when they're not being used.
So it's like putting them in a little energy-saving sleep mode.
Exactly. If you're not using your Wi-Fi, boom, the I/O subsystem can tell the Wi-Fi card to power down completely until you need it again. Same goes for Bluetooth, your webcam, even the backlight on your keyboard. All those little things add up.
It's like a little energy efficiency ninja working behind the scenes to save my battery. I never would have thought about it that way.
It's pretty impressive stuff. And it's not just about your laptop or phone either. Think about those massive data centers with thousands of servers running 24/7. Power management there. Huge deal.
That makes sense. The less energy they use, the better for everyone.
Exactly. And the I/O subsystem plays a key role in that. It's all connected.
Wow. We've covered some serious ground in this deep dive. Who knew the I/O subsystem was so fascinating?
Right. It's easy to take technology for granted, but when you peek behind the curtain like this, it's amazing to see how much complexity goes into making our digital lives work.
Absolutely. So to our listeners out there, we hope this has given you a newfound appreciation for the silent symphony happening inside your devices. Next time you open an app, stream a movie, or even just print a document, take a moment to think about the I/O subsystem, working tirelessly behind the scenes to make it all happen. Until next time, happy computing. All right, strap yourselves in. Today's deep dive is going to take us down a rabbit hole you might not expect, all from clicking on something as simple as, well, a file on your computer.
Yeah, it's one of those things you never really think about, right? Like,
No.
what's actually happening under the hood to make that little icon magically open up into whatever you need?
And trust me, the magic is definitely there, but it's the kind of magic that's even cooler once you understand the mechanics behind it. It's like, comparing a magic trick to like a perfectly engineered watch. Both impressive, but for different reasons.
100%. And just like you don't need to be a watchmaker to appreciate a good timepiece, you don't need a computer science degree to get this.
Exactly. So consider this your backstage pass to the fascinating, surprisingly intricate world of how a computer actually goes about reading a file.
It's a journey, that's for sure, and one that most people, even those of us who work with tech every day, don't think about too often.
Well, we're going to change that today. And to help us navigate this digital jungle, we have our expert who's going to break it all down for us.
Happy to be here. Always love a good deep dive.
So let's set the stage. Say I'm on my computer and I click on a file called, let's say, deepdivenotes.txt. What's the very first thing that happens?
Okay, so right off the bat, your computer sees that file name, that deepdivenotes.txt, but it's not treating it like the actual data, more like a clue.
A clue. Okay, I'm intrigued.
Think of it this way. Imagine you're looking for a specific book in a massive library, right?
Right.
You wouldn't just wander around aimlessly, would you?
Chaos. Total chaos.
Exactly. And
Yep.
that's where the file system comes in. It's basically the library's card catalog.
Ah, okay, I'm starting to see it.
It takes that file name, our clue, and translates it into a physical location on your storage device, like a specific shelf in a specific aisle.
So I'm picturing those old card catalogs with the little drawers and index cards.
Spot on. Now, imagine that library has multiple floors, each with its own catalog. That's where the mount table comes into play.
Okay, so it's like a map, right? Telling the computer where each floor is.
Exactly. Each floor represents a different storage device, maybe your hard drive, a USB stick, whatever. The mount table is how the operating system keeps track of what's plugged in where.
Makes sense. So we've got our file name as a clue, our card catalog to guide us, and our map of the library floors. What's next?
Well, now we need to find a librarian who specializes in that particular section, right? And that's where device drivers come in.
Device drivers, like specific ones for different types of storage.
Bingo. Each device driver knows how to communicate with a specific piece of hardware. Your hard drive has one. Your graphics card has one. Even your webcam.
So it's like each librarian has their own little system, their own way of finding things on their floor.
Precisely. And to make sure the right librarian gets called, our computer uses these things called major device number and minor device number. They're like unique IDs for each piece of hardware.
So if I'm understanding this right, the operating system uses those numbers to match up the request with the right driver.
You got it. It ensures the right set of instructions gets delivered to the right piece of hardware. Think of it like a well-oiled
Library system. I love it. Okay, so we've officially navigated the library, found our section, and alerted the right librarian.
And that, my friend, is only the beginning.
Oh, I know, and this is where it gets really good. But we're gonna have to take a quick break. Don't worry, we'll dive into the actual data transfer process right after this. Stay tuned. And we're back, folks. Before the break, we were knee-deep in file systems, device drivers, the whole shebang. We basically tracked down the right librarian with our file request.
Right, we've got our metaphorical Dewey Decimal System all figured out.
Exactly. But the million-dollar question is, how does the actual information, the stuff inside the file, actually get moved from the storage to, well, wherever it needs to go?
It's a bit more complicated than just beaming it over, right? Although that would be pretty cool.
Sci-fi episode for another day. So walk us through it. What happens next?
Well, our source material calls this next stage a blocking read system call. Sounds technical, but it's basically the point where those software instructions we've been talking about, they turn into real physical actions.
Okay, so our librarian knows what book we want, but now they have to physically go get it.
Perfect analogy. And this is where the real unsung hero of our story steps in. The kernel.
The kernel. It's a word everyone's heard, I feel like, but few actually understand.
Well, think of the kernel as the ultimate multitasker, the stage manager of your entire computer system. It's managing resources, making sure everything runs smoothly.
So in our library scenario, the kernel is
making sure the lights are on, the bookshelves are organized, that kind of thing. But most importantly in this case, it's optimizing how that data gets delivered.
Optimization. Is reading from a hard drive really that inefficient?
Well, it can be. So the kernel uses something called a buffer cache. It's basically a temporary storage space in RAM. Much faster to access than going back to the hard drive every time.
Ah, so it's like keeping copies of the most popular books in a special section near the front desk.
Exactly. Saves everyone a lot of time and effort.
Ah.
Now, while the kernel is handling all that, our device driver, the one we talked about earlier, it's busy writing up instructions for the actual data transfer. It's telling the hardware, okay, copy these specific bits from this sector of the hard drive over to this location in memory. Very specific instructions.
Wow, this is a lot of back and forth. So the CPU, the brain of the computer, is handling all of this, right?
You'd think so, and it does play a role, but it turns out having the CPU manage every tiny bit of data transfer, it's actually pretty inefficient. Like trying to conduct a whole orchestra while playing every instrument yourself.
Okay, so what's the solution? How do we get more instruments playing at the same time?
Direct memory access, or DMA.
Okay.
It's like giving certain tasks their own dedicated conductor, so the CPU can focus on the bigger picture.
So DMA is like, don't worry, CPU, I got this. You go ahead and do your thing.
Exactly. DMA takes those detailed instructions from the device driver and manages the data transfer between the hard drive and memory directly, without needing to constantly interrupt the CPU.
Wow, so that's why even if I have a super fast processor, a slow hard drive can still slow things down.
Exactly. It's like having a high-speed train that has to stop at every little station along the way.
That's a great analogy. So DMA is handling the heavy lifting, but it's still following the game plan laid out by the device driver.
Precisely. It's a beautifully choreographed system. And the really mind-blowing part is, it's not even set in stone. Remember how our source mentioned something about operating systems being able to load device drivers dynamically?
Right, like they can learn new tricks as they go.
Essentially. It's like if in the middle of a play, someone wheeled out a prop no one had ever seen before, and the stage manager just rolled with it.
I gotta say, I'm starting to see why they call this stuff computer science and not just, computer messing around.
Right. There's some serious elegance to how it all works.
It really is. I mean, before we started this deep dive, I thought open a file was about as basic as it gets. No, forget about it.
It's like that saying, the more you know, the more you realize you don't know.
And right now, my brain is feeling very aware of how much it doesn't know, but in a good way, in a way that makes me appreciate all the amazing things my computer can do even more.
That's what we love to hear. It's all about that sense of wonder.
Speaking of wonder, we got to talk about this whole dynamic loading thing some more, because that's where things get really meta, wouldn't you say?
Oh, absolutely. It's like the operating system is a jazz musician just riffing along, figuring things out on the fly. New device, no problem. Just got to find the right groove.
And that's what allows our computers to keep up with all the crazy technological advancements, right? Like, I don't have to buy a new computer every time someone invents a new kind of gadget.
Exactly. Well, not just because of this, but it's definitely a huge part of it. Imagine if every time you plugged in something new, you had to manually install a whole bunch of software just to get it to work.
Oh my goodness, the flashbacks to like the early days of printers, not fun.
Exactly. But with dynamic loading, the operating system can do a lot of that heavy lifting for you. It sees the new device, figures out what it needs, finds the right drivers,
The right librarian. I love that analogy.
and suddenly, bam, your computer knows how to talk to this new piece of hardware like it's been best friends all along.
That is so slick. Really, when you think about it, it's kind of the definition of plug and play, isn't it?
It is, and it's a beautiful example of how hardware and software have to evolve together to keep pushing the boundaries of what's possible.
So, as we come up for air from this deep dive into the inner workings of our computers, what's the one takeaway you hope our listeners walk away with?
That's a good one. I'd say next time you're staring at that little loading icon, that spinning wheel of doom, instead of getting impatient, take a moment to appreciate the absolute symphony of processes happening behind the scenes.
Oh, I love that. It's like instead of focusing on the wait time, focus on the wonder.
Exactly. Because there's a lot to be impressed by, even in those everyday tasks we take for granted.
Couldn't agree more. Well, on that note, it's time for us to say goodbye, but not before thanking you, our incredible expert, for taking us on this wild ride.
Always a pleasure to share my love of all things tech.
And to our listeners, as always, keep those curiosity engines running. We'll see you on the next deep dive.
Ever get that spinning wheel of doom when you're trying to stream a movie? You know, like the internet's stuck in rush hour or something. Well, deep down in your computer's code, there's this ingenious system called Streams that's working hard to prevent those digital traffic jams. And that's exactly what we're diving into today, how Streams brought order to the chaotic world of data. We'll unpack how they work, why they matter, even if you wouldn't know a line of code from, well, a straight line. Ready to build a better data pipeline. Imagine, if you will, data flowing through your computer like water through pipes. You've got your faucet, the pipes themselves, and that refreshing glass of water at the end. So in the Streams world, that trusty faucet is called the stream head. It's the point where your program taps into that data flow. And just like we've got different pipes for different jobs, think garden hose versus kitchen sink streams have these cool things called stream modules.
These modules were revolutionary because of their flexibility. They really changed how software was made. Think of each module as a specialist. One might be all about handling what you type on your keyboard, another's an encryption expert, scrambling data to keep things secure, and another might format everything to look good on your screen.
It's like having a whole team of specialists hidden inside my computer. No wonder it can juggle so many things at once.
So we've got the faucet, these adaptable pipe sections, but what about that final step? You know, what directs the data to the right spot, whether it's my screen, a network card, whatever?
That, my friend, is the job of the driver end, the final puzzle piece in our data pipeline. What's amazing is that before Streams came along, programmers had to write new code every time they wanted to use a new device or protocol. It was like building a whole new engine every time you wanted to drive a different car. Talk about a time suck. It's incredible how something as fundamental as Streams revolutionized how we use computers.
Absolutely. Streams made operating systems adaptable and extensible, all thanks to this standardized, modular approach to data. It's like having that universal adapter works with any device, anywhere. Pretty slick, right?
Okay, so we've got our data flowing smoothly through this elegant system of pipes and modules, but what happens when it's not smooth sailing anymore? Like, what about when my internet connection throws a fit because I'm trying to download a huge file while streaming a movie? It's like everything just grinds to a halt.
Well, that's where the real brilliance of Streams comes into play. They've got this built-in system called flow control that prevents those digital meltdowns.
Oh, Cardi troll, huh? So Streams basically play traffic cop with my data.
Exactly. Imagine there are these little waiting areas between each section of pipe. We call them queues. These queues act as buffers, so one module doesn't overwhelm the next with too much, too fast.
So it's like putting those strategically placed rest stops on the highway to prevent those massive pileups.
You got it. And just like those rest stops have signs that say full, modules in a stream can actually talk to each other. They use these things called control messages, kind of like traffic signals.
Oh, I see.
They can be like, hold your horses, I need a sec to catch up. Or, okay, send the next batch through.
So that's how we avoid data getting lost in the shuffle. just because one part of the system is overwhelmed.
Precisely. Flow control ensures that data moves smoothly through the entire pipeline. In fact, one of the examples they use in the original paper on this really brings it home: network cards.
Oh yeah, network cards. Those are like the mailboxes for all our devices, right?
Yeah.
Handling all that incoming and outgoing internet traffic.
Exactly. Now, picture your physical mailbox overflowing because you're getting way too much mail at once. Some of it's going to end up on the floor lost.
Lost mail is a nightmare. I can only imagine what lost data is like.
And that's where streams come in to save the day. With flow control, our network card can send a message back up the pipeline. Something like, "Whoa, hold the mail. My buffer's full. Need a minute to process everything."
Talk about a lifesaver, or a data saver, I guess you could say. That is such a smart way to handle that problem.
It really highlights the elegance of streams. They thought ahead and designed a solution for a problem most people don't even realize is happening. Flow control is all about ensuring data integrity and reliability, which is crucial for, well, everything we do on our computers these days.
So we've explored this whole world of streams, acting like a well-organized plumbing system for all our data. But let's zoom out for a sec. Why should any of this matter to someone who's not, a coding guru?
That's the thing about streams, right? They've kind of quietly shaped the digital world we live in, whether we realize it or not. Remember how we talked about programmers having to, reinvent the wheel every time they wanted to add a new device?
Yeah, before streams. Total nightmare fuel.
Totally. But by creating this standardized system, it unleashed this wave of innovation, all because data could flow freely.
So it's like, instead of needing a completely different engine for every type of car, we've got one versatile engine. It can power anything with a few tweaks.
Exactly. And that's what happened in computing. Streams paved the way for all these devices and software we use, everything from smartphones to those supercomputers.
Wow, so something as simple as organizing data flow had that big of an impact.
It's wild, right? It just shows how important those unseen layers are. You never really think about your plumbing until something goes wrong.
And nobody wants to deal with that.
Exactly. Streams, they're like the unsung heroes, making sure our computers can handle everything we throw at them.
So next time I'm binge watching my favorite show, gotta thank streams for keeping things running smoothly. It really goes to show sometimes the simplest solutions are the most powerful. And with that, we've reached the end of our deep dive into the fascinating world of streams. We hope you've enjoyed exploring these hidden depths with us. And one last thought before we go. Imagine you could design a brand new streams module. What amazing problem would it solve? What kind of innovation would you bring to this elegant system? Something to ponder. Until next time, keep exploring the wonders of tech. Ever feel like your computer's dragging its feet, even when you know it's got a top-of-the-line processor?
It's frustrating, right?
Today, we're doing a deep dive into the world of input-output, better known as I/O.
Yeah, I/O.
We're going to try to understand why it's so key to unlocking your computer's true performance.
Absolutely.
We're going to be looking at some technical articles, research, all that good stuff, but
Don't worry, I'm here to break it down.
yeah, I've got my trusty expert here to make sure we all stay on the same page.
Always happy to help.
Okay, so I/O. In the simplest terms, it's how the different parts of your computer talk to each other.
Right.
Your central processing unit, memory, hard drive, your keyboard, your mouse, everything.
It's the communication highway.
Think of it as like the network of roads and highways,
Yeah.
keeping everything connected.
That's a great analogy. And just like a highway, things can get a little congested. This is where we run into I/O bottlenecks.
Bottlenecks, like when you're stuck in traffic.
Exactly. Let's say you're remotely logging into another machine,
Okay.
or your computer is trying to access a ton of files scattered across your hard drive.
Yeah.
These operations can overwhelm those I/O channels, and everything just slows down.
So it's like having a Formula One race car,
Okay.
but you have to stop for gas every few laps.
Yeah.
All that power, but you're still held back.
Precisely. And this is where it gets even more interesting. Our sources point out that as hardware has evolved, we've got faster processors,
Right.
larger storage. The pressure on I/O subsystems to keep pace,
Of course.
it's grown tremendously.
So we're building these more powerful engines.
Yes.
But we're still relying on the same old roads.
Exactly.
No wonder things get backed up.
And to really visualize this, let's turn to figure 12.8.2 in the research.
Yeah.
This graph does a fantastic job of showing the performance gap that's developed between different computer components.
Okay, let's see what this graph is telling us.
Yeah.
Wow. It's pretty clear that while CPU and memory speeds, they've skyrocketed.
Oh, yeah.
But the speed of storage devices, especially hard drives, They haven't kept up. It's like they're stuck in the slow lane.
It happens.
So knowing this, what can we actually do to optimize I/O and get our systems running at their full potential? I'm ready to break free from these bottlenecks.
Thankfully, our sources outline some strategies. They lay out some key principles for what they call I/O efficiency. I think you'll find them quite insightful.
Okay, let's hear them. Give me the secrets to a speedier computer. Make me an I/O master.
Okay, so the first principle, it's all about something called context switching. So imagine you're laser focused on a task and someone keeps interrupting you with questions or, just like little things.
Yeah.
It takes time and energy to switch gears and get back on track.
Right, the worst.
Sure.
Especially when I'm like, really in the zone? Don't people know better than to interrupt then?
Right. Well, the same principle applies to computers. Excessive context switching, it can really bog things down.
Really?
Each time your CPU has to switch between those different tasks, it's time, it's resources.
So you know how frustrating it is to get interrupted when you're on a roll?
Yeah,
That's what too much context switching is doing to your computer.
exactly.
Got it. Okay, what's next?
Next up is reducing data copying.
Okay.
Every time data has to be moved around, it takes time. It's like if you have to make multiple trips to bring in groceries from your car,
Oh, tell me about it.
much faster to just consolidate it all into one trip.
Like the king of the one-trip grocery run. Efficiency is key.
There you go.
What else can we do to keep those bits flowing smoothly?
The third principle is about minimizing interruptions.
Okay.
So instead of interrupting the CPU for every tiny little bit of data,
Yeah.
we can use larger transfers or even something called polling techniques. It's about, again, bundling things together, being more efficient.
So instead of like ringing the doorbell for each individual letter, you get the whole package delivered at once.
Exactly.
I like the way you think.
Now, it's important to note that polling isn't always the perfect solution.
Cool.
Because if the CPU is constantly checking for data that isn't ready yet,
Yeah.
it can be a bit like waiting for a pot to boil,
Yeah.
You're just constantly checking, you're wasting energy. It's about finding that sweet spot.
Trade-offs. There's always a balance. Okay, so one more principle to go, right? And this is where you mentioned earlier something about like moving processing like directly into hardware. That sounds kind of intense.
It is. This is where things get really fascinating. Because sometimes for the absolute fastest I/O, we need to offload some of those processing tasks from the CPU to dedicated hardware, like device controllers.
So instead of the general contractor, you bring in a specialist.
Yes.
Like you wouldn't hire a whole construction crew just to fix a leaky faucet.
Precisely. It wouldn't make much sense, would it?
No.
So while that dedicated hardware can offer a huge speed boost,
Right.
it's not always the most practical or cost-effective approach.
So it's a balancing act. Figuring out the right tool for the job. Makes sense to me.
Right.
But before we get too far ahead of ourselves here,
Sure.
let's bring it back to our listeners, right?
Yeah.
If someone's, they're dealing with a slow computer, what's one like concrete thing, one thing they could try based on, what we've discussed?
That's a great question. I would say start by figuring out where that bottleneck is. Is it slow storage? Is it network latency? Is it something else?
Right.
Once you've identified the culprit, then you can start exploring targeted solutions based on these principles we've been talking about.
This has been, wow, a real eye-opening deep dive, I gotta say, into like the inner workings of our computers. I feel like I've been given like a backstage pass
Right.
to a high-speed data center or something.
It really highlights how crucial I/O is to, everything we do on our devices.
Right.
Every click, every swipe, every video stream, it all relies on efficient data transfer.
Totally. It makes you appreciate that intricate dance of hardware and software.
It is.
That's just happening behind the scenes every millisecond. But speaking of exciting developments, you mentioned earlier that the world of I/O and computing performance, it's always evolving, right?
Always.
What's on the horizon? Any new tech that we should be like keeping an eye on?
Absolutely. One development that has the potential to really shake things up is the rise of what's called non-volatile memory, or NVM for short.
NVM. Okay, that rings a bell. Is that the super fast storage? That's like starting to become more common.
Exactly. Unlike traditional hard drives, which have those physical spinning disks to read and write data, NVM devices are entirely electronic.
Okay.
They can access data at speeds that are closer to your computer's memory, which is a game changer for I/O.
Wow. So we're talking about a significant speed boost here.
Oh, yeah.
Does this mean like we're on the verge of a future where those pesky I/O bottlenecks, they just become a thing of the past?
It's certainly a possibility. As NVM technology matures and becomes more affordable,
Right.
it could really reshape how we think about data storage and access.
I can imagine.
Imagine a world where booting up your computer or loading complex programs, it happens almost instantly.
Now that's a future I can get behind. It sounds like we're on the brink of a major shift in computing.
We are. And that brings us to a final, kind of thought-provoking question for our listeners to ponder. How do you think these increasing speeds of NVM and other emerging technologies will impact the future of I/O and computing performance in general?
It's a question worth considering. And, as we've learned today, what happens in this kind of hidden world of I/O, it really does have a huge impact on our digital lives.
So the next time you're waiting for a file to load or a program to open, remember that intricate world of I/O at work. You might be surprised by how much there is to discover.
You said it. Thanks for joining us on this deep dive into, really, the heart of computing performance. Until next time, keep those bits flowing.